Okay, thank you. Okay, I need to continue. Okay, so thank you for having me. So the paper I present today is this one, which is about Supernova-scope for the direct search of supernova axions. I'm Jiaming Zheng, and I'm now a postdoc in Zhengbao Li Institute and Shanghai Jiaotong University in China. So Axion is a very well-motivated model. It not only solves the strong CP problem, it can be a nice dark matter candidate, and it may also relate to baryogenesis. And what is more interesting to us in this talk is that it couples to nucleons and photons and leptons in various ways so that it can be searched for in many different ways. So what we are interested in particular is this Axion Helioscope. So the original idea is that the axion can be produced in the sun via the Primakov process. And then if the axion travels into the helioscope, it will be converted into X-ray by this strong magnetic field inside the magnetic ball. And then this X-ray photon will be picked up by the X-ray optics. And this is how a helioscope would discover the solar axion. But there are other axion sources in the sky. And in particular, we could imagine that there might be a nearby supernova inside the galaxy. And the axion can also be produced from the supernova by bremsstrahlung of the nucleons. And in this case, we might also want to point an helioscope towards the supernova, and then the axion will be converted into gamma ray in the same way as in the helioscope, in the regular helioscope. And this use of helioscope is what we call the Supernova-scope. And the subject of this talk is all about this Supernova-scope. When shall we point the Supernova-scope to some of the supernova candidates? And which progenitor should we point to? How we should do it? And what is the prospect of studying physics by doing it? So as for when shall we point the helioscope towards supernova, as the star evolves to its end and to its final stage that is going to core collapse, the supernova neutrino will become more and more abundant, and about 1 hour or even a day before the core collapse, the pre-supernova neutrino will be strong enough to be picked up by current or future neutrino detectors. For example, the Super Kamiokande, the Complant, which are already running, or the future neutrino detector, Juno. So we just used the result from this very nice review of pre-supernova neutrino. So these neutrinos can be observed in these current detectors for supernova within 300 parsecs and about 1 hour before the core collapse. And that's only for the normal ordering of neutrino mass hierarchy. For inverted ordering, the perspective would be quite bad, actually. But normal ordering is more probable according to the current observation anyway. The situation would be much improved in Juno. So it can detect supernova within 700 parsecs and about 20 to 70 hours in advance of the core collapse. And this is for both normal ordering or inverted ordering. So we are quite sure that we will be able to see the pre-supernova neutrino if there is nearby supernova. And what's even better is that these neutrino detectors will be included in the supernova early warning system. So the way it works is that if these detectors detect pre-supernova neutrinos, it will send information to the server of this new system. And then this new system will in turn send out messages to subscribers, so the scientists can point anything they want to do science with this supernova. So now, which supernova progenitors should we look at? We have just said that the neutrino detector can only detect pre-supernova neutrino for near candidates, and that's why we apply a cut for that the distance of the progenitor should be within 250 parsecs from the Earth, and actually this is also good for observation with helioscopes. And we further apply the rule that the mass of the progenitor should be larger than 10 times the solar mass. And that's because for lighter supernova progenitors, the pre-supernova neutrino are mainly undetectable. And applying these two rules, we are only left with 6 candidates. And the position of them in the sky is shown in this figure. So for current neutrino detectors, such as CAMLAND and SuperCAMLConde, it has quite bad angular resolution, and maybe we can only guess 1 out of these 6 candidates, and there's 16% of chance, and that's not bad actually. But with Juno, which is a very large detector, it would be able to reach an angular resolution of about 60 degrees. And in this case, we will be able to tell, for example, Betelgeuse or ENIF apart from the other candidates. And if the scintillator in Juno is further improved by, say, adding lithium doping, then it would be able to have an angular resolution of about 15 degrees. And then we might also be able to tell these apart from each other. So the helioscopes are originally designed to chase the sun, so it cannot rotate freely in the vertical direction. So there is a worry that whether it can actually be pointed to the supernova candidate or not. And actually, take IAXO as an example. Its maximum elevation is just 25 degrees, meaning that it can look up or down by at most 25 degrees. We calculate the fraction of time that it is able to look at each progenitors. And we find that for the current proposal of the IAXO, you will be able to observe the candidates more than 50% of the times. This is shown by the dark blue color here. And if this maximum elevation of the helioscope is improved to 50 degrees, then for 4 out of the 6 candidates, it will be able to observe them 100% of the time. So if one of them is going to explode, IAXO would not miss it. We can further dream about the situation that there is another helioscope at another position on Earth, and that will further increase the coverage. So after we showed that it is possible to look at the supernova at the right time, we calculate what is the expected number of events in this coupling versus axion mass plane. So these blue counters are one event counters, which the solid ones are the 1 event counters, and the dashed lines are the 100 event counters. The blue contours are drawn for Spica, which is the closest candidate in the list. And the red contour is drawn for Betelgeuse, which is the furthest candidate in the list. And everything in between will have a contour in between these two lines. And I will just mention two features of this contour. The first one is that the Supernova-scope will be able to probe much heavier axion than the helioscope, and that's because the energy of the supernova axion is about 70 MeV, and it is much larger than the average solar axion energy. And this makes the axion goes out of phase from the photon at a much larger axion energy. And if the axion turns out to be light, the prospect for the supernova-scope is about the same as the helioscope. So in this case, we would expect that if a solar axion is observed by the helioscope, then it would be very, very probable that it would also be observed by the supernova-scope. And then the supernova-scope will be a powerful tool of probing supernova physics. Finally, I would like to mention a design of the gamma ray detector that would be used to detect these gamma ray photons from the supernova axion. So the model of the design is the following. So we propose to collect the gamma ray signal by stacks of scintillation plates made of cesium dioxide. And these scintillation plates are wrapped around by plastic scintillator used to withhold the background muon that comes from the side of the detector. So the main background now is reduced to the cosmic ray muon that comes directly from above. So how can we separate these cosmic ray muons and the gamma rays? So here we show a histogram of total deposit energy for the gamma ray photon on the left-hand side and for muons in the right-hand side. So for photons, we choose some particular energy of several tens of MeV, which is the typical energy of the supernova axion. And in the right-hand side, the energy of the muon are chosen to be several GeV. And less energetic muon would have a hard time reaching the sea level, so we don't worry about it. So there are two lessons that we can learn here. So first of all, the photons would deposit nearly all the energy inside the detectors. And so it only penetrates several plates here. And second, the muon will penetrate the whole detector, so it only deposits part of its energy. So there are two ways to distinguish the muon from the gamma ray photon. One is that we can just see how much is the total energy deposit. And then these two kind of signals can be separated efficiently. And the other way is to count the number of plates with more than 1 MeV energy deposit. Since photon only penetrates several plates, this count would be much less than that of the muon, which penetrates all the plates here. So here's a summary of the talk. I hope that I have shown you that the next galactic supernova within 300 parsec can be forecast, and it can be pointed to by IAXO for more than 50% of the time. And this percentage can be even increased if the maximum elevation of the helioscope is increased to 50 degrees. And the supernova scope will typically probe much heavier axion than helioscope. And even for the case of light axion, then it is likely that both axion and both solar or supernova axion will be discovered if any of them is discovered. And this makes it a powerful tool to study the supernova physics. And the dominant background would be the cosmic muon, but it can be efficiently rejected. And the last message I would like to pass is that the nearby supernova is so rare, and it is um, about once every several decades for the galactic supernova, and even rarer if it is a nearby supernova. And that's why we want to get prepared for it and to do all kind of science with it, with this very rare opportunity. And hopefully we can see a nearby supernova in our lifetime. And that's all. Thank you.